Our next presentation is by Richard Shoge from M12, North Carolina State University. And it's going to be the development of a hyperelastic model for the material properties of porcine patellar cartilage.
Actually, my title has changed just a little bit, but it's still going to involve the hyperelastic theory. It's actually development of an impact model of cartilage degeneration, and my department's actually at North Carolina State and at University of North Carolina, Chapel Hill, go Tar Heels, big game today. But it's going to incorporate hyperelastic theory and designing parameters for cartilage for our experiments. But so the purpose. What am I doing? One is we want to identify mechanical factors that initiate osteoarthritis. Osteoarthritis is when your cartilage degenerates over time and it results in bone-on-bone contact, a lot of pain. It's a very debilitating disease, and I'll show you some stats later of why it's very important. We're using the porcine model, and turns out, well, porcine model, why? Because where pig cartilage is very accessible. Turns out there are, I think, what, 2 to 3 pigs for every human in North Carolina. But they have a lot of pig farms, but no, what's most important is there are a lot of similarities between some of the parameters in pig cartilage and human cartilage as far as the specific genes we're looking for and proteins and those sort of things. So the experimental steps involved in this process is, one, of course, we want to determine the cartilage mechanical properties. So when you're taking a material and you apply a load to it, it's going to deform. So these cells are going to respond to this deformation in a specific way. So we got to understand how cartilage is going to deform under a given load in order for us to make a connection with that load and the cellular response. So we're using an impact experimental model. Why is that? We're creating this traumatic event, this blunt trauma to the cartilage surface, and it's able to simulate or recreate what one would see in beginning stage osteoarthritis. Of course, it'd be nice to study the disease progression over 20, 40 years, but that's not possible. You won't get funding for that. And I'm trying to graduate. So, so we want to speed the process up a little bit, and we can do this with our impact model. I'll go into the details about that later. And once we can determine these mechanical properties of cartilage, we can determine the local stresses and strains within the impaction region. And then once we have an idea of course, not going to be pinpoint accuracy across each single patella, but we're going to get a general idea of the stresses and strains that these cells are seeing and get a good idea of what are causing these cells to either die off or upregulate these proteins that are involved in cartilage matrix degeneration. And that's the last point right there. We want to correlate the mechanical and the biological response. So let's go into the details. Brief intro, cartilage. There are 3 main cartilage types within the body. What we're mostly interested in is the group on the left, hyaline cartilage. This is the cartilage that is found within our joints. Its function is functions as mainly as a shock absorber, and it creates this low friction environment within our joints. So it's very important. It's an innervated tissue, so it's under all this load all day when you're running around, when you're jumping. But once it starts to degrade and you have this bone-on-bone contact, your bones are highly innervated, so that's when you get the pain. The pain sets in. So its function is highly dependent on the integrity of the cartilage within the joint. So what makes up this structure? Cartilage is a very complex material. It's a biphasic material. It consists of a solid phase, which is a porous matrix. This consists of collagen, which gives it great tensile strength, proteoglycans, which are these proteins and polysaccharides that have a highly negative charge. So, of course, when you put 2 like charges together, they're going to repel. This will give cartilage its excellent compressive properties. And then there's cells within cartilage, also called chondrocytes, that are responsible for maintaining the integrity of the cartilage matrix. And what's also important to its properties are the fluid phase. And this is predominantly water, and then you have some anions swimming around there too. But when you have this fluid phase that's trapped within this porous matrix, and you apply a load to it, it's going to create drag within the porous matrix. So this drag is going to cause, is going to increase the compressive strength of cartilage. Sorry, I'm going a little bit fast here. I'm just trying to make sure she doesn't put up the red flag. Cartilage degeneration, this is just a general picture of what happens when cartilage degenerates, bone-on-bone contact. It'll create bone spurs, pain, and all that good stuff, bad stuff, excuse me. But it has no precise known cause. These are just some numbers, some stats of why it's so important. 21 million Americans affected, that's a lot. There are treatments available. There's, and they'll inject steroids or hyaluronin, which will help and decrease some of the friction within your joints. But you have to do those every 3 weeks to a month, so it's only temporary. Serious case, you got joint replacement surgery, or they'll even do cartilage replacement, where they'll take cartilage from a non-weight-bearing surface and then put that in, replace that in the areas that are affected. But this is short-term also, and there's integration issues with the new tissue and the old tissue. So there is no known cure or long-term treatment solution for osteoarthritis. We're more interested in prevention. As I said before, prevention is better than cure. It's multifactorial causes, biological, chemical. We're focusing on mechanical and joint injury. So these impacts to the joint, an example would be, say, a car accident or a severe athletic injury, are predisposing factors to osteoarthritis. So what we are wanting to look at was, we wanted to look at normal or perpendicular forces and tangential forces, shear forces that will cause cells to degenerate within cartilage. So this is just some information on what's been done in the past. You can do, there are in vivo studies, in vitro with explants. You can look at one single impaction, which we did, or multiple impactions in a cyclical manner. But what these studies have done before is they've only looked at the forces perpendicular to the surface of cartilage. And as I said before, we want to look at what do these perpendicular forces and these tangential forces and due to the cartilage matrix and the cartilage cellular response. So you don't have to read the whole thing here, but hypothesis is just that, all right, the damage to we believe damage to the cartilage matrix is going to be greatly affected by these shear forces than the normal perpendicular forces, and that chondrocyte cell death is going to increase with these shear forces and protein loss, and that some of the degradative enzymes will be upregulated more in the shear impactions than the normal impactions. So our experimental design, we're creating this blunt impact to the articular surface. We have two sets of impactions. One is normal to the surface, one and done, that's it. And then we also we apply a normal force, and then we slide the surface of the cartilage underneath our impacting rod, and then that creates this shear force also. And we're looking at one specific strain rate. This strain rate, 25 millimeters per second, creates the sort of damage that one would see in initial stages of osteoarthritis. And it's, as I said before, it's a one and done impaction. So this is just a picture of some of what one would see after our impacted load to the cartilage surface. To the right, B and C, they both experience the same load magnitude, about 2,000 newtons, it's about 500 pounds. But for one, we added this sliding motion. In B and C, it was just normal to the surface. And so as you can see, even though they experience the same load magnitude, we have a lot more damage to the cartilage surface in B than in C due to the shear loads. And of course, that can be attributed to friction and then increased loading. But so, explained before, we're looking at a porcine model, and we're comparing normal and shear impactions to control surfaces. And we'll also culture these cells up to 14 days. And we're going to look at some of the histological data also. So during our experiments, what we can record are the axial, we record forces in the 3 directions and the displacement on the surface of the cartilage. And then we're going to look at collagen staining, proteoglycan, apoptotic cells, which is cell-mediated death, and also specific genes and proteins that are involved in maintenance of the cartilage matrix. And this is just some of the raw data that we would get after each impaction. The two top graphs, one on the right is just a force versus time of the axial impaction, and on the left is the shear impaction. And the 2 bottom ones are the respective tangential forces to the surface that one would see. And to the left, of course, the 2 plots on the left, even though the axial forces are around 2,000 newtons, which is about 500 pounds, with that shear force, when we add that component, we're going to get a significant difference in the shear forces that one would see in the shear impaction versus the axial impaction. So we can see what effect this additional shear force would account for as far as cellular response. Now, forgive me, I'm going to kind of speed through the next slides, but I hope you get a general gist of what our aim of the study was. So forgive me, but you can catch me afterwards for any additional questions, and I can talk my head off for the next couple days. 5 minutes? Okay. Oh, thank you. All right. Excellent. So, all right. So, as I said before, we're recording the forces on the surface of the cartilage. We want to understand the stresses within the thickness at the actual locations of these chondrocyte cells. So we need to develop an analytical model that's going to incorporate these material properties, which we have to determine, and then and there are different ways we can go about this. There's a linear elastic model. Elastic just means that once you apply a load and you release that load, that object is going to return to its original shape. Linear elasticity doesn't really apply for us because that only works with small strains, and we're looking at larger strains. Hyperelasticity accounts for this larger strains, and then it also accounts for a nonlinear relationship between stress and strain. Now, viscoelastic modeling is probably the most robust type of model for biological tissues, in the fact that it can account for nonlinear behavior, but it also accounts for the time-dependent properties of tissues, but it's definitely more complex. So for ours, we chose, I'm gonna skip through here real quick. We chose a hyperelastic model just because simply we're not looking at the time-dependent properties. We're looking at the instantaneous response of the cartilage to this impact load. So we pretty much, cartilage can be broken down into 3 major zones. They have different structure, and so they're going to have different properties. So we need to determine the properties for the 3 different zones of cartilage. So we did tensile and compressive tests of the different regions. The surface region is more stiff. It has a higher concentration of collagen fibers. They pretty much have the same, close to the same compressive moduli, but I'm going to skip here real quick. And so we wanted to fit a function to this data so that we can incorporate it into a finite element model. And we chose the Ogden hyperelastic function. This function is based on strain energy. And it showed a better fit than, there are many hyperelastic models to choose from, Mooney, Rivlin, Yao, but this one seemed to fit our data better than the others, and has shown success in the past in fitting data with these sorts of properties. And then this is just some of the fit that we got. In red is the model, and then the blue is the data, of course. But what I'm doing now is that once we have these properties determined, we want to incorporate these properties into a finite element model. Unfortunately, we can't just take the entire patella and the cartilage thickness and work some math equations. It's a little more complicated than that. Of course, you need the same amount of unknowns as you need equations, but there are just way too many unknowns in our case. So what we have to do with finite element programs or analysis is just a tool that we use where we can break down a large surface into smaller elements and analyze each of those elements, the stress and strain distribution in each of those elements, and then incorporate that into a larger model. And of course, the more elements you have, the more accurate your model is going to be. But it also means the more computationally expensive the model is going to be. So we have to find a medium ground where we don't, where we can still have an accurate model, but we can be able to solve the problem within a reasonable amount of time also. So to conclude, once we're still in the stages of creating this finite element program, but once it is all said and done, we want to be able to find correlations between these stresses and strains within this impaction region with cell viability, genes and proteins that are involved in cellular matrix integrity. And then the long-term goal is to, if we can determine the mechanical factors that cause cartilage degeneration, well, what can we do to either stall or reverse the effects of these mechanical factors? So if we're upregulating some matrix enzymes, maybe there's a way to inhibit these enzymes. All right, I'm done. Thank you very much. So cartilage thickness is around 2 millimeters, so about 2 to 5 millimeters. So it's pretty thin, and we're using patellar cartilage, so it can be thinner in other regions. So, and of course, the age of the specimen is gonna play an effect also. And usually we use very young specimens, so we get a really thick, a much thicker cartilage dimension thickness. But well, it does, but it's very slow. I mean, I'm sure athletes, you know, injure themselves. I mean, and not just athletes, everyday people can. But yes. So, but it's a very slow process. Cartilage within your joints, especially the knee, is in a capsule. There's no blood supply. So chondrocytes rely on diffusion to receive the materials that they need. Thus, it's going to take a lot longer than, say, any other cells within the body. So, yeah. Thank you very much.